Chapter 1. The title of Chapter 1 is Converting the Earth's Resources into Useful Products. The Earth's resources could be considered as reactants, and also useful products could be considered as products. So, the process to convert the Earth's resources into useful products could be said to be simply reaction. In these courses, I'd like to use an abbreviation of the reaction like RXN, so reaction. So, chemical reactions are at the heart of chemical processes. This is the catchphrase of this chapter 1. Okay, keywords you will learn from this chapter. Chemical processes chemical processes are reactions plus separation plus additional processes. And then let me focus on the reaction because this chapter is about the reaction. So here is the chemical reaction equation. A plus B reactant is going to C plus W. C is desired product and W is waste product or byproduct. Of course, each entity of this chemical reaction equation has its own stoichiometric coefficient. Alpha for A, beta for B, chi for C, omega for W. And also, we could think about the value added. The money, I mean. Of course, in the practical balanced chemical reaction equation, you don't need to think about the dollar. However, you are the chemical engineer, so we should think about the additional value production. So this is the chemical reaction equation. So in this chemical reaction equation, all keywords you will learn from this lesson, this chapter, are there. Raw materials, reactants, or products, or waste products, and some money. You will learn how to complete a preliminary assessment of the quantities of raw material required to produce a desired product. So raw material, product, and we are thinking about the quantities. The other thing is about the waste products, about the W, the quantities and also identities of waste products. And plus, we are going to the dollar. The process economics related to money with choosing raw materials and chemical reactions. Those are the keywords of this chapter 1. Questions. Just let me read them and you will learn you could answer these questions after you have learned this chapter. What raw materials are available? So you will choose raw materials, cheaper, better, and eco-friendly, better, or something like that. How can chemical reactions be combined into pathways to effectively convert raw materials to products? You will design some chemical reaction pathways in this chapter. How much raw materials is consumed? It's a very important thing because this is closely related to money. What byproducts are generated, and if these byproducts are harmful or not eco-friendly, we need to have an additional cost to remove them. What are simple measures, some parameters for comparing the economic and environmental impact of different raw materials or chemical reaction pathways. So we'll design chemical reaction pathways and we'll choose raw materials to decrease the cost. So economic value, of course, which is the money, but environmental impact or hazardous problem is closely related to the also money. So we should think about the dollar there. Okay, so this is the very first subchapter of this chapter 1. Let me think about chemical process again. Definition. The chemical process is the process to convert raw materials into desired products by changing the physical-chemical properties of the raw materials. That is the definition of a chemical process. So here's several simple examples. We can convert waste materials into useful products. Okay, here's the 10 kilogram milk, and then I'd like to make a cheese. Then from 10 kilogram milk, we could get 1 kilogram cheese and plus wheat. Wheat is a kind of the waste products made during the process of cheese production. So this kind of waste product would be discarded. However, we can find a very valuable protein in wheat. What is that? That is the lactoferrin, and lactoferrin is used for infant formula to improve iron uptake. So by using the wheat, we can make a very valuable product, which is lactoferrin. Of course, in this case, we need to have a chemical process. The other thing, vincristine. I'm not accustomed to this chemical, but this chemical looks like this one, very complicated structure. And this vincristine, the very small amount of vincristine is found in the periwinkle plant. This is the periwinkle plant. So after concentration and purification of this vincristine, then we could obtain a powerful drug for treating leukemia and cancers. So we could increase the values of the product. Also, here's the combustion reaction. Some carbon sources like natural gas or oil or coal plus oxygen is going to some CO2 and H2O and some hazardous SOx and NOx, and plus we could generate some energy heat. So by using this energy, we could generate the electricity. Anyway, this combustion reaction for generating electricity could be considered as the chemical process. Okay, next one. How can we design chemical processes? In this class, we will use the other word, synthesize. Synthesize means design in this course. So again back, how can we synthesize chemical processes? 3 steps will follow. Define the product requirement. Of course, choose raw material. So define this one and then choice of this one, and then let's go to the center. Select chemical reactions and physical operation. We should think about the chemical process. Okay, here I'd like to give you more detailed example of chemical processes. What kind of things could be produced from crude oil? Let me follow the chain of production. Petroleum exploration and production. So we could get the crude oil. This is a kind of chemical processes. And then via petroleum refinery, we could separate some chemicals from the others. So in this case, I have got benzene. And then by using benzene, we could produce phenol. So this is another chemical process, is commodity chemicals production process. And then phenol is converted to bisphenol A by combining two phenols. So it looks like that. This is phenol and some alkane between the phenols. This is so-called bisphenol A. By using this bisphenol A plus some other monomers, we could make the plastics and polymers. This one, that is the polycarbonate. This is another chemical process. And then by using this material, polycarbonate, we could make something like airplane windows, eyeglasses, baby bottles, and bicycle helmets in the plastic fabricators plant. So this is the chain of chemical processes, and then you can find a lot of products between the chemical processes. This is the first example of chemical processes. Here is the second example of chemical processes, which is the chlor-alkali industry or chlor-alkali process. Chlor indicates chlorine. Let me check it. Chlor indicates chlorine, Cl2, and alkali indicates some hydroxide, for example, sodium hydroxide. So in this chlor-alkali industry or process, we could make the Cl2 and sodium hydroxide at the same time. Okay, here's my pointer. So what kind of process is used? This is the electrochemical process. There is a chamber and we have two electrodes. And also we have two compartments here and there. Between those two compartments, we have some membrane. So onto the left compartment, 26% sodium chloride salt or solution is introduced into this pipe. And then chloride minus, let me change again, pen is better. So chloride minus negative ions is oxidized on this electrode, then finally it is going to chlorine gases. Then through the output pipe, 24%, that is to say, dilute solution of sodium chloride is going out of this chamber. Let's go to the right side of compartment of these reactors. Water is introduced into the system, and then on this electrode, there is some change, like H2O is reduced to hydrogen gas. And then you could get the hydrogen gas. At the same time, H2O is converted to OH minus. So at the same time, sodium plus ions, excess sodium plus ions is moving through this membrane. So finally, we could obtain sodium hydroxide in the unlit line of the right compartment. So at the same time, by using the electrolysis, we have sodium chloride and sodium hydroxide. Okay, so by using the chlorine gas, we could make the pulp and paper, solvents, plastics, pesticides, antifreeze, and refrigerants. Also, sodium hydroxide, so-called caustic soda, is used for making soap, dyes, fibers, papers, drugs, and rubber or something like that. Okay, one more things. There are three largest, let me change to the pointer. There are three largest inorganic chemical industries. The first one is actually almost the same, the level of size. The first one is chlor-alkali process. The second one is ammonia process. The third one is sulfuric acid process. Okay, let's go to the third example of chemical processes. We could use some biomaterials as the raw materials. So the title of this example number 3 is From Corn, the raw materials, to fiber, the desired product. Most of carbon-based materials are made from non-renewable fossil fuels. So for example, some polymers um, are made from some coals or crude oils or some natural gas or something like that. Everything is non-renewable fossil fuels. However, DuPont developed a new process to synthesize fibers from renewable resources, which are cones. Here's cones. So corn is the very low material, and by using the fermentation, having engineered bacteria, this corn is converted into 1,3-propane diol. So this fermentation process is the chemical process. And then by using this 1,3-propane diol, we could make some polymers. Then from these polymers, fibers can be made, and also finally we could make some clothes. So this is a kind of renewably sourced polymer, which the name of which is DuPont Sorona, this one. So we have one biochemical process, and the other thing is another chemical process, and then finally some manufacturing of clothes. Until now, I have explained about the chemical processes, the definition of chemical processes, and some examples of chemical processes. And then it's time to go to the other subchapter. Here's the subchapter number 3, balanced chemical reaction equations. So, or CRE. CRE stands for chemical reaction equations. Here is one example of chemical reaction equation. Actually unbalanced chemical reaction equation, because we don't have any stoichiometric coefficient is here. Tetrachlorosilicon plus hydrogen, and then silicon, tetrachlorosilicon is reduced into just silicon plus hydrochloric acid. This is the unbalanced CRE, or chemical reaction equations. Then let me try to balance these CRE, chemical reaction equations, after evaluating the stoichiometric coefficient for each entity of CRE. It's very easy and you can do it. So here we have one silicon, so one silicon, no problem. And then we have 4 chlorine in the left hand side, so you should have 4 chlorine on the right hand side. 4, and right now you have 4H, but in the left hand side you have only 2H, so you should multiply 2 in front of H2. That's it. That is the balanced chemical reaction equations, right? But sometimes you can change the stoichiometric coefficient by multiplying some values. So by the factor 2, the stoichiometric coefficient of silicon tetrachloride is going to 2. And 2 is going to 4. Also 1 is going to 2, while 4 is going to 8. Also it is right. The other thing, at this time, the factor a half, you do have this kind of stoichiometric coefficient for each entity for no. So you have this kind of stoichiometric coefficient for each entity. So let me define the convention of the sign of the stoichiometric coefficient. So, okay, here's the stoichiometric coefficient. Sometimes I can say nu I, nu with subscript I. This is the Greek letter. It pronounced nu. And I means the entity or molecule of the chemical reaction equation. So sometimes silicon tetrachloride, sometimes H2, sometimes silicon, or hydrochloric acid is I here. For example, in these chemical reaction equations, let me change it to the pointer. So nu tetrachlorosilicon is 1/2, but you should recognize minus signs in front of this value. So I mean, again, this a half is going to there, but this is the reactant. So in that case, you should add minus. That is the convention in this textbook. Also, nu HCl. HCl is here, and then stoichiometric coefficient is 2 with plus because HCl is product. So the convention of stoichiometric coefficient is like that: negative for reactant, positive for product. The next thing is stoichiometric balance equation. Chemical equation stoichiometrically balanced, I can say like that, only if this balance equation is satisfied. This equation means the numbers of each atom is the same between left hand side and right hand side of the equations. So what is the meaning of this equation? Let me try to understand. So the summation of species I have said I is the entity of CRE. Let me write down. I is entity or molecule of CRE. So for example, I should be silicon tetrachloride and proton or silicon or HCl. Okay, that is the I. And then do I, of course, let me change it. Do I is stoichiometric coefficient of each entity. What is the epsilon subscript H and I? So again back here, it is called epsilon, which is Greek letter, and I still indicates the entity of CRE. What is the H? H is the element, for example, silicon or chlorine or hydrogen or something like that. So epsilon with the subscript H and I is number of atoms of the element H in compound I. So let me get one example. If H is equal to chlorine in these chemical reaction equations, then we could have this kind of stoichiometric balance equations. So what is that? So epsilon chlorine with silicon tetrachloride means number of chlorine in tetrachloride silicon. So what's the value? Again, the number of chlorine in the tetrachlorosilicon. So the answer is 4. 4 chlorine atoms existing in this tetrachlorosilicon. So here's 4. And by the stoichiometric coefficient of the corresponding entity, so minus 1 over 2, then plus, let's go to the other entity. In the second entity, H2, there are no chlorine atom, so you don't need to think about that. How about the third one? No chlorine, so you don't need to think about that. And then let's go to the last one, HCl. You have one chlorine gas, no, you have one chlorine atom in this hydrochloric acid. So epsilon with chlorine in HCl is 2. This is product, so this is the no. The epsilon of chlorine in HCl is 1 because you can find only single chlorine atom in HCl. So this number is 1. So this guy is going to this one. And also it's time to count the stoichiometric coefficient of the corresponding entity. That is the plus 2. This should be plus because HCl is product. So here is the plus 2. So the summation of those two things is equal to 0. Then I can say this equation is well balanced in terms of chlorine gas. Of course, you should move to silicon and also you should move to proton for satisfying the stoichiometric balance equation. Okay, let me think about how to balance chemical reaction equation systematically. So there are 4 steps to balance chemical reaction equation. So I'll let you experience the 4 steps by using example. Example number 1, oxidation of methane to CO2 and water. This is a kind of combustion process. So unbalanced chemical reaction equation is methane plus oxygen plus CO2 plus H2O. And of course, you should add the stoichiometric coefficient like that. New CH4 in front of CH4 and O2 this one, CO2 this one, and H2O this one. That is the first step. So I mean the first step is to write down unbalanced chemical reaction equation without the stoichiometric coefficient. Let's go to the second step. Here are stoichiometric balance equation. So in this unbalanced chemical equation, you have 3 kinds of atoms: carbon, proton, oxygen. The other is the same. So you have 3 different atoms are there. It means we will get three different equations in terms of stoichiometric balance equation. Okay, let's try to make those balance equations. The first equation is about carbon. And then you can find only one carbon there with the stoichiometric coefficient. This stoichiometric coefficient is unknown and also target we want to calculate. The second, we are still on carbon, so there are no carbon and 0 with stoichiometric coefficient of O2. And one carbon, 1 with CO2 stoichiometric coefficient. And no carbon there, 0 with the corresponding stoichiometric coefficient should be 0. Let's move to the second atom, hydrogen. So from the viewpoint of hydrogen, this kind of stoichiometric balance equation should be satisfied. So in the first entity, you can find 4 atoms of hydrogen, so 4 with stoichiometric coefficient, and 0 hydrogen with coefficient, 0 hydrogen with coefficient, and 2 hydrogen with stoichiometric coefficient should be 0. Let's go to the oxygen, the last element used in this chemical reaction equation. So 0 oxygen in the first one with coefficient, 2 oxygen with stoichiometric coefficient, and 2 oxygen with CO2 coefficient, and 1 oxygen with H2O coefficient should be 0. So right now we have 3 equations because we have 3 atoms, carbon, hydrogen, oxygen, and also we have 4 unknowns. So we have 4 entities in this chemical reaction equation, so 4 unknowns. Degree of freedom 1. I means if a number of unknowns is more than the number of equations, we cannot solve this problem. So in this case, you should set up the basis. In this case, I have chosen the methane, this one, the raw material, one of the raw material, as the basis. Then it should be -1 for the simple calculation. Why do you have minus? Because methane is the reactant. So I have fixed one unknown. In this problem, the stoichiometric coefficient is unknown. Then, right now, 3 equations, 3 unknowns. Then you can solve this problem. So final result is like that, and final balanced equation is here. 1CH4 plus 2 oxygen is going to 1CO2 plus 2 H2O. Here is the second example, which is the adipic acid synthesis. Here is the adipic acid. We have 4 carbons there, and at each end we have a carboxylate. This adipic acid is the intermediate used in the manufacture of nylon, so it's very important chemical. So let me just follow the 4 steps we have just learned. So the first step is unbalanced equation. For making the adipic acid, we have 4 reactions. The first one is cyclohexane is oxidized into cyclohexanol. Cyclohexane looks like this one, and cyclohexanol is like that with alcohol. And also the cyclohexane oxidation is going to sometimes cyclohexanone. This one is cyclohexanone, and this one. So again, cyclohexane is oxidized into sometimes cyclohexanol, sometimes cyclohexanone. this one. So right now we have two different intermediate. So let's start with the first intermediate, cyclohexanol. Cyclohexanol is reacted with nitric acid, and finally this reaction goes to adipic acid. Or cyclohexanone, the second intermediate, is reacted with nitric acid and it is going to adipic acid. So right now we have four reactions, and then we'll follow the four steps for each reaction. Okay, let me start with reaction 1. Step 1, unbalanced chemical reaction equation. So this equation is already given to you. Cyclohexane, oxygen, cyclohexanol plus water. So step 2, stoichiometric balance equation. You know, in this equation, we have three different atoms there: carbon, hydrogen, oxygen, those things. Also the same thing, carbon, hydrogen, oxygen, or hydrogen, oxygen. So we have three different atoms in this chemical reaction equation. So we expect we'll have three stoichiometric balance equation. And also we need to calculate four different stoichiometric coefficients because we have four entity here, 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 here. So four unknowns. Then let me try to set up the stoichiometric balance equation. Let me take carbon first, and then we have 6 carbon in the first entity, so 6 with coefficient. And in the second, you cannot find any carbon, so you can ignore the second term. And the third one, C6, so 6 with the corresponding coefficient, plus no carbon in H2O, so you can ignore them. So the summation of those two terms is going to 0. And then let's move to proton. So 12 proton with coefficient, and nothing there, ignore this term. And 12 or so with coefficient, and 2 hydrogen with coefficient should be 0. And then from the viewpoint of oxygen, no oxygen, ignore. 1 oxygen, no, 2 oxygen with stoichiometric coefficient, plus 1 oxygen, 1 here with coefficient, plus 1 oxygen with coefficient should be 0. So right now we have just set up the stoichiometric balance equations. So 3 equations plus 4 unknowns. So you need to have one more equation, or you should fix one unknown. So let's go to the third step, basis setup. So let me take the basis. Let me take the cyclohexanol as the basis. Of course, you could set up water or oxygen or cyclohexane as the setup, as the basis. So depending on you, anything's okay. But in this case, I have take the cyclohexanol as the basis. So new cyclohexanol is equal to +1. Then after fixing one of unknown or stoichiometric coefficient, then we have 3 equations and 3 unknowns. So degree of freedom is 0. Then we can calculate it. So the result is like that, and final balanced CRE. Okay, let's move to reaction 2. The unbalanced one was cyclohexane is oxidized into cyclohexanone plus water. And in the same way, you can set up this kind of equations with 4 unknowns, and basis setup would be followed. In this case, cyclohexane is taken as the basis. So you should write down nu with C6H12 is equal to 1, but it should be -1 because cyclohexane is the reactant. And then right now 3 equations plus 3 unknowns. Then you can calculate these equations, the multiple equations with multiple unknowns. Then final result is like that, and this is the balance equations. Here is the reaction 3. The first step, unbalanced CRE, cyclohexanol, is reacted with nitric acid, and finally go to adipic acid with nitrogen oxide plus H2O. That is the unbalanced CRE. And let me count the number of entities and number of atoms. Here's number of atoms: carbon, hydrogen, oxygen, and also nitrogen. 4 atoms are involved in this unbalanced chemical reaction equation. So you can expect 4 equation. And how many entities are there? 1, 2, 3, 4, 5. So 5 unknowns. Then you can set up this stoichiometric balance equation here. And of course you need to set up the basis, because degree of freedom of this system is 1. So in this case, I have set up the cyclohexanol as the basis. So nu cyclohexanol is equal to -1, because cyclohexanol is the reactant. And then right now for equation with 4 unknowns. So we could calculate the stoichiometric coefficient. Then here's the final answer. Until now, let me change it to laser pointer. And until now, you have tried to get the information about the stoichiometric coefficients. And at the first step, you have solved the problems of multiple linear equation with multiple unknowns. Maybe you could solve the problems, but sometimes you have a lot of stoichiometric coefficients are there, and a lot of atoms are involved in the chemical reaction equation. Then sometimes it is a little bit more difficult to solve the problem. So we need to have a systematic method to calculate the multiple linear equations with multiple unknowns. That is the Gaussian elimination method, or GE. GE stands for Gaussian elimination. So the GE is the method to solve the problems of multiple linear equations with multiple unknowns. So here is one single example of multiple linear equation. 3 equations with multiple unknowns, 3 unknowns. Then how can we solve this problem more systematically? As the first step, make the matrix. So you have 3 unknowns. This is unknown vector u with w, and the stoichiometric coefficient matrix 1, 1, 1 here, 1, 2, 2 here, 2, 3, 4 here, actually -4 here. And also you have another constant on the right hand side of the equation. So 6, 11, 3. This is called the constant vector. So A matrix and then X vector is equal to some vector. So right now we have the matrix representation of the multiple linear equations with multiple unknowns. Then how can we solve these problems? Our target is to make this coefficient matrix in a reduced triangular form. The reduced triangular form have non-zeros on the diagonal plus zeros below the diagonal. I mean, 1 should be 0, 2 should be 0, and 3 should be 0 in this section. So how can we convert this coefficient matrix into the reduced triangular form. So let me operate something. So the first column is still here, and then let's try to this entity as 0. So the row 2 minus row 2 minus row 1. So 1 minus 1 going to 0, 2 minus 1 going to 1, 2 minus 1 going to 1, and also 11 minus 6 is going to 5. So then right now we have 0 here. The next target is this one, number 2. So row 3 minus 2 by row 1. Row 3 minus 2 by row 1. So 2 minus 2 is going to 0. 3 minus 1, 3 minus 2 is going to 1. Minus 4 minus 2 is going to minus 6. And 3 minus 12 is going to minus 9. Okay, then it's time to go to erase this one value. Then I'd like to row 3 minus row 2. Row 3 minus row 2 is 0 minus 0 is going to 0. 1 minus 1 is going to 0. Minus 6 minus 1 is going to minus 7. Then finally we have a form of reduced triangular. So that's it. And then it's time to convert this matrix representation into the equations. So this one is 0, 0, minus 7w is equal to minus 14. And 0, v plus w is going to 5. And u plus v plus w is going to 6. Then you can easily calculate and obtain the unknowns. Let's start from the last one. So w is 2, and then input 2 into the w. So v is 3, and then input 2 for w, 3 for v, and then finally you can easily obtain the value of u is equal to 1. This is the Gaussian elimination method to solve the problems of multiple linear equations with multiple unknowns systematically. You have just learned about the Gaussian elimination method to calculate the multiple equations with multiple unknowns. So let me apply this Gaussian elimination method to real chemical reaction equations. This equation is the reaction 3. You have learned about that. And cyclohexanol plus nitric acid is going to adipic acid plus nitrogen oxide with water. So in these equations we have 3 atoms: carbon, hydrogen, oxygen. Okay, one more thing, nitrogen. 4 atoms. So you will have the 4 different the stoichiometric balance equations: 1, 2, 3, 4, and 1, 2, 3, 4, 5. 5 unknowns are there, which are the stoichiometric coefficients. So we should set up one of the unknowns as the basis. So in this case, stoichiometric coefficient for the cyclohexanol is set up on the -1. So this equation is changed into here. 6 with -1 plus the same. 12 with -1. This is -1. So let me get together all constant number on the right hand side. So the first equation is like that. And the second equation is minus 12 is going to the right side, so 12. And then minus 1 is going to the right side, right hand side of the equation, then plus 1. So right now we have four different equations and four unknowns after fixing the first stoichiometric coefficient. Then it's time to make some matrix representation of these equations from here to there. Right now we have four unknowns. We have fixed the stoichiometric coefficient of the first entity, so nu2, nu3, nu4, nu5 are four unknowns. So in these unknown vectors you have nu2, nu3, nu4, nu5. Also, in the constant vector you have 6, 12, 1, 0. 6, 12, 1, 0. And then let me check the matrix, the coefficient matrix. After fixing the first entity, then we have four columns of the coefficient matrix. So the first one is HNO3, second one is adipic acid, third one NO, and fourth one is water. So let me put the numbers into this matrix, coefficient matrix. So let me start with the carbon, and there are no nitric acid, so 0. And then adipic acid, 6 here, so 6, 0, 0. No NO and no H2O in this stoichiometric balance equation from the viewpoint of carbon. And then let's move to hydrogen. So 1 HNO3, 1 HNO3, and 10 adipic acid, no NO here, and then H2O, 2, 2. How about oxygen? 3 HNO3, and adipic acid, 4, and NO, just 1, H2O, 1. And let's go to the last atom, which is nitrogen. So nitric acid 1, and then no adipic acid here, and 1 NO here, and no H2O 0. So right now we have complete the matrix representation of these problems. So it's time to solve this problem by using Gaussian elimination method. I'd like to remind you that we will make the reduced triangular form. So what is the definition of reduced triangular form? Non-zeros on the diagonal and zeros below the diagonal. So we'll make those entities in the triangular matrix will be 0. However, the other requirement is non-zero zeros on the diagonal. But unfortunately, we have 0 on the diagonal here and there. So I will remove the zeros on the diagonal at the very first time, and then I'd like to make the zeros in this triangular. Okay, here again, the same matrix representation of the reactions. So my primary or first target of the operation is to remove zeros on the diagonal. So the first operation is exchange rows 1 and 2. So 1 and 2 exchange it. So this one is going to the first, and this one is going to the second row. So right now I remove this 0. So right now I have 1. Then it's time to remove 0, this one. After exchanging rows 1 and 4, 1 and 4, this is going to the first row, and this is going to the fourth row. So right now we don't have any zeros on the diagonal. Then it's time to zero all entities of the triangular matrix. Maybe you can do it following this operation, and this operation, and this operation. Finally, you can have the reduced triangular form in this matrix. Then you can calculate the unknowns. So nu 5 is equal to 7 over 2 divided by 3 over 2. So the value is like that. And then after inputting the value of nu 5 into the second equations, then you can get the value of nu 4. Then by using nu 4 and nu 5 into this equation, and then nu 3 would be obtained. But in this case, we have a lot of zeros, and then just nu 3 is 1. 6 nu 3 is equal to 6 without any values of nu 4 and nu 5, so nu 3 is equal to 1. After we are getting those three values, then of course we could calculate the values of nu 2 by using these equations. Then this is the final balanced chemical reaction equation. Okay, so right now you could balance the chemical reaction equations. Then it's time to go to the other subchapter number 4, generation consumption analysis, or shortly GCA. So GCA stands for generation consumption analysis. GCA is the systematic method for synthesizing or designing reaction pathways with multiple chemical reactions. What is the target of GCA? Is to make the most product. This is the first requirement. And out of the least raw material, this is the second requirement, with fewest byproduct. This is the third requirement for the target. Of course, this is the very of course thing, because we want to have more amount of product from smaller amount of the reactant with suppressed byproducts, of course things. So in this generation consumption analysis, we'd like to synthesize the best performance process. Okay, here's an example, Leblanc process to produce sodium carbonate here, and we have three equations. Salt, sodium chloride, and sulfuric acid are heated to produce sodium sulfate. It could be a kind of intermediate plus HCl byproduct, and this sodium sulfate is converted to the sodium sulfide by the help of carbon. CO2 is generated, which is byproduct, and this sodium sulfide as an intermediate is going to sodium carbonate by the help of calcium carbonate. Calcium sulfide would be the byproduct. So we'll use two measures, which is very important thing. The ratio of reactant to product. So if you could decrease this value, then your process is considered to be better thing. So RP ratio. The second one is byproduct per product. So of course you don't want to have byproduct in your upstream. So if you have a small number of BP ratio, it is good thing. So let's do it. Let's do the generation consumption analysis. So from the stoichiometric coefficient, we could expect how my chemical process working very well or not. So here is again balanced chemical reaction equation, three equations, and then let's make the stoichiometric coefficient table. The first column lists the compounds included in the chemical reaction equations: sodium chloride, sulfuric acid, sodium sulfate, HCl, and sodium sulfate again I have written down already. Carbon here, sodium sulfide here, CO2 here, sodium sulfite again here, so calcium carbonate here, sodium carbonate here, and calcium sulfide here. So we have just listed the compounds on the first column. On the first row, list the reactions. So R1 and R2 and R3. Then in the main body of this table, put the stoichiometric coefficients. For example, sodium chloride of R1 is -2. Sulfuric acid of R1 is -1, like that. Sodium sulfate +1, HCl +2. That's it for the reaction 1. And then let's move to the reaction 2. So the first, the entity of the reaction 2 is sodium sulfate. So here's the sodium sulfate. It's the stoichiometric coefficient of the sodium sulfate is -1. Then carbon -2, sodium sulfite, and CO2. Then let's go to the third reactions. -1, -1, 1, 1, -1, -1, 1, 1, something like that. And then, okay, right. Now you have completed the stoichiometric coefficient table, but one more column should be added for final calculation. In the rest column, put the value obtained after summation of all stoichiometric coefficients in the same row. So sodium chloride is just low material, so it appears in the R1 column. So -2 is just going to -2. So let's go to the other things. How about sulfuric acid? In the R1, this is generated. However, in the R2, this is consumed. So sulfuric is going to 0 as the net sum. So this kind of compound can be classified into the intermediate. At the very first time, you don't have it. And also at the final time, you don't have it. So that is considered to be intermediate. HCl, and let's go to the other thing. Sodium sulfide, also intermediate. And then sodium carbonate, +1, something like that. Okay, so from the last column, we can read the reactant consumed and product generated. So minus sign means reactant. Plus sign means product. So let me check it. Reactant consumed. So minus, so I means let's try to get the minus values of net summation. So -2, 2 moles of sodium chloride is consumed. -1. 1 mole of sulfuric acid is consumed. How about -2, this one, carbon, and calcium carbonate -1, right? So 1 mole of calcium carbonate is consumed. So totally 6 moles of reactant are consumed. Then let's go to the product or byproduct part. So plus sign indicates product. So this is the first positive one, and 2 more HCl, 2 more CO2, 1 more calcium sulfide, and as the final product 1 more of sodium carbonate. So those three guys can be considered as byproducts. So totally byproducts 5 more and product just 1 more. So let me calculate the RP, reactant product ratio, which is 6. 6 divided by 1. How about byproduct to product? 5 to 1 is going to 5. Here is the question. It is possible to synthesize a better process by using different raw materials or combining different reactions? Of course, why not? In the previous example, I have introduced the Leblanc process, which produces sodium carbonate. In this second example, also I'm trying to produce sodium carbonate, the same product, but I want to use different process. This process is so-called solvay process. And also, here are a series of chemical equations for this process. I'd like to group 3 different categories. So in the first group of reactions, I'll try to make the carbon dioxide and ammonia. Those two materials are used for making bicarbonate in the second group of reactions. And then finally, in the third group of reactions, this bicarbonate is combined with sodium plus, then finally we could get the sodium carbonate, the same product of Leblanc process. What is the objective of this example? I'd like to compare between the Leblanc process and the Solvay process in terms of RP ratio and BP ratio. So let me get some detailed explanation of this reaction. Limestone, calcium carbonate, decomposes to lime. Calcium oxide is the lime. Then also carbon dioxide is produced in this reaction. And this calcium oxide or lime react with water to form milk of lime. Calcium hydroxide is milk of lime. And then this milk of lime is going to there react with ammonium chloride then to make ammonia. This is another target of this group of reactions. Ammonia plus some byproducts like calcium chloride and water. So right now, by using the calcium carbonate as the raw material or very initial reactant, we have made CO2 and NH3. Okay, the other raw material is NH4Cl. So anyway, our target materials obtained from this first group of reaction was CO2 and NH3. Then let's go to the second group of reactions. In the second group of reactions, ammonia is used. That ammonia is coming from the first group of reactions. Ammonia plus water, actually ammonia dissolved in water, makes ammonium hydroxide, which reacts with CO2. Of course, CO2 is coming from the first group of reactions. CO2 to make ammonium carbonate, and then one more carbonated, one more carbonation, then we have ammonium bicarbonate. So finally we have produced bicarbonate. Here is the carbonate source, and our final product was sodium carbonate. So this bicarbonate is used for making the final product. Let's go to the third group of reactions. This one is going to there. Ammonium bicarbonate is reacted with sodium chloride, another raw material. It's going to ammonium chloride and sodium bicarbonate. And then sodium bicarbonate is converted to the final product, carbonate, sodium carbonate, plus CO2 and water. That's it. That is the series of reactions for making sodium carbonate in the solvate process. So right now we have the balanced chemical reaction equations for the solvate processes. So it's time to go to the second step. Let's make the stoichiometric coefficient table here. And at the first column, I am listing all of the compounds included in the solvate processes. For example, calcium carbonate, calcium oxide, the other raw material is sodium chloride, and the product sodium carbonate. And then here is the 8 reactions. Each reaction columns you could fill out the stoichiometric coefficients of the balanced chemical reaction equations, something like that. So right now we have the matrix of the stoichiometric coefficient for the solvate process. Then at the last column we have net summation. So for example, calcium carbonate -1, only -1 for reaction 1, so just -1. Well, let me go to the ammonium chloride. -2 for reaction 3 means ammonium chloride is consumed for making something. And also in the reaction 7, ammonium chloride is produced. So the net summation of ammonium chloride is -1. It means ammonium chloride should be added into the reactors as the raw material. Anyway, right now we finalize the stoichiometric coefficient table, and then from the last column of this table we could measure and estimate the parameters of Rp and Bp. So let me check the Rp value first. R for reactant and P for product. So let me check the minus sign because minus sign indicates reactant. 1, 2, 3, 4, 5. 5 reactants are consumed during the solvate process. At the same time, 1 mole of sodium carbonate is produced. So 5 per 1 is equal to 5. The value of Rp is 5. How about byproduct? So where is B? Positive sign indicates the side product, byproduct, or desired product. Water is side product. And the other thing, ammonia, the byproduct. 2, 3, ammonium bicarbonate. And then 4, calcium chloride. So 4 moles of byproducts are produced during this process for making 1 mole of sodium carbonate. So the BP ratio is 4. Let me compare those values with the values of Leblanc. Leblanc had Rp at 6, BP at 5. But right now, the solvate process provides Rp at 5 and BP at 5. The measures are decreasing when we have adapted the solvate process. So I can say the solvate process better than the Leblanc process because we need to have the smaller amount of reactant and also smaller amount of byproducts are produced. So again, the Solvay process is better than Leblanc process when we are thinking about the RP ratio in terms of reactant and BP ratio in terms of byproduct. Okay, so right now we have a better process, which is the Solvay process. But still, we have an opportunity and chance to improve Solvay process by designing those equations. So let's go to the other step, which is target setup. My objective and my target is to remove ammonia containing compounds in the products in the original Solvay process, because ammonia containing compounds are a little bit hazardous. So let me check what kind of ammonia containing compounds in the tables. Ammonium chloride, ammonia, ammonium hydroxide, and ammonium carbonate and ammonium bicarbonate. Okay, so I'd like to kill those things, which means these values should go to zeros, just zeros. So net production or net consumption should not be guaranteed. The other target is I want to have only calcium carbonate and sodium chloride as reactants, like in Leblanc process. So I want to kill the other thing, sodium bicarbonate as reactant. So if we do this thing, then we could have only sodium carbonate as products. Maybe or not, I'm not sure. But anyway, we can kill a lot of side products there. So I want to achieve this target, and then I'm trying to have something. Okay, so the blank list, ammonium chloride, right? So it was the reactant, so I'd like to change it into zero. Ammonium is a byproduct, but I want to make it zero. Ammonium hydroxide as the reactant will be zero. And ammonium bicarbonate, okay, originally it is zero. Then ammonium bicarbonate plus 1, it should go to 0. Sodium chloride, we won't touch the sodium chloride because it is the original raw material. And then sodium bicarbonate, I want to make it 0. So after we making those things to be 0, then what is the value of Rp? Let me expect it. So in that case, let me check the R, minus sign, minus 1, nothing, 2. So 2 over 1 is equal to 2. And then how about byproduct? Byproduct, check the positive sign. So 1 byproduct, which is the water, they will be 0, and the other thing is calcium chloride. So BP ratio is 2. So 5 is going to 2 for in terms of RP, and 4 is going to 2 in terms of BP. So if we can do these things, making zeros, then we could improve the original Solvay processes. One more things. Our original target is that we have only sodium carbonate as products. But here is the water, and here is the calcium chloride as the product. Even if I have synthesized this network of reaction pathways. Why? Uh, water, it is nothing. If you find water molecules in the output stream with sodium carbonate, there are no problem. So I don't take care of the water molecules. Of course, if we could make it 0, but it is nothing. How about the other thing? Calcium chloride, okay, if we can make it 0, that's great. However, let take the stoichiometric coefficient of the table here. Only one single entity. The calcium chloride is generated by reaction 3. we cannot touch this case. I means only the case in the for the only case when we have some generation term and consumption term, then we can make it zero by adjusting the reactions. However, in this case, I means the calcium chloride case, this materials is only generated, not consumed. So we cannot touch it. We cannot make it zero. So plus 1 is just going to plus 1. So we should let calcium chloride as the byproduct. Step 4. It's time to calculate the weight factor of reactions by using chi calculation. This is the step 4 of generation consumption analysis. The objective of chi calculation is to make the entry in net column 0 for ammonia containing compounds plus an unwanted product like sodium bicarbonate for the solvate process. So let's go back to the matrix or table, stoichiometric coefficient table, and still we have the list of the compounds and reactions. One different thing is this one, chi values. Chi value is a kind of the weight factor for each reactions. Chi 3 indicates the weight factor for reaction 3, chi 4 for reaction 4, chi 5 for reaction 5, something like that. First, let me check the compounds. Those are in my blank list, right? Excluding sodium chloride. So we will touch 1, 2, 3, 4, 5, 6, right? 6 compounds, and 6 compounds is related to the reaction 3 to 8, except of reaction 1 and 2. So I take care of only those 6 reactions. Then I put the chi 3, chi 4 to chi 8 above the reaction 3 to reaction 8. And this is the weight factors for each reactions. Actually, each the stoichiometric coefficient of each reactions. Okay, so right now reaction 3 have this kind of stoichiometric coefficient. R4, this one, 5, 6, 7, 8. And then let's set up the zero net equations to calculate the values of weight factors. So the first compound I'll take care of is ammonium chloride, then minus 2 by chi 3 plus 0, 0, 0, 0, 0 and plus 1 by chi 7 should be 0. Of course, originally minus 1, but we will make it 0. So for the ammonium chloride, this equation is derived. How about ammonium? 2 by chi 3 plus minus 1 by chi 4. It should be 0. The third guy, plus 1 by chi 4 plus minus 2 by chi 5. This one should be 0. And in the same way, you could derive the zero net equations for ammonium carbonate, ammonium bicarbonate, also sodium bicarbonate. Then, right now, we have 6 equations because we have a plan to touch 6 compounds. And the number of unknowns are 6 because those items or compounds are closely related to those 6 reactions. So we should have the 6 unknowns for which is the weight factors for the reactions. Degree of freedom is 0, and then you could calculate it. This is very simple. Sometimes you could use the Gaussian elimination method. Then four kites are 1. So it means nothing changes there. However, chi4, the wave factor of reaction 4 and 7 is 2. So we will multiply this factor into these reactions, reaction 4 and reaction 7. Then let's go to the next step, process synthesis. I mean, it's time to calculate. I mean, it's time to apply those wave factors for calculating the net summation of stoichiometric coefficient. Right now, the wave factor of reaction 4 is 2 and 7, 2. So the stoichiometric coefficient of those reactions should be changed. Originally, the stoichiometric coefficient of reaction 4 was -1, -1, +1. However, right now, -2, -2, +2. After we applied the factor 2 into the reaction 4. In the same way, the stoichiometric coefficient of R7 is going to +2, -2, -2, +2. Originally, they were +1, -1, -1, +1. Okay, that's it. And then let's try. Let me calculate the net summation of stoichiometric coefficient again. Those values are coming from the previous slide. I mean, before doing the process synthesis or before applying the weight factors. And then this is the new value. Anyway, let me calculate it. So calcium carbonate is consumed in the reaction 1. Actually, calcium carbonate is the original raw material, and also it is not affected by reaction 4 and reaction 7, so nothing changed. In the past, -1, right now, -1. Calcium oxide in the same way. CO2 in the same situation. And how about the H2O? Actually, we didn't take care of the H2O. However, reaction 4 affects the H2O. So the value is changing. It is going to 0. Fortunately, the original value was +1, but right now it is going to 0. So this was not our intention. However, with our luck, we could remove the water side product. Calcium hydroxide, no impact by R4 and R7. Now let's go to the main body of the black list, actually that yellow list here. Ammonium chloride, -2 original value and +2. After applying the factor 2 into reaction 7, going to 0. Ammonia, original value, and then weighted value is going to 0. Ammonium hydroxide, weighted value, original value is going to 0. Ammonium carbonate, originally it was the 0. And also, this compound was not affected by reaction 4 and reaction 7. So, anyway, 0. Ammonium bicarbonate, original value +2, and then adjust value -2 by applying the factor 2 of chi7. Then it's going to 0. Sodium chloride, we didn't touch it, and also we cannot touch it because this is the single entity, only consumption. Sodium bicarbonate, and the corrected value and original value is going to 0. Calcium chloride, we didn't touch it, and sodium carbonate, we didn't touch it. Okay, that's it. So so let me calculate the RP and BP value in this new improved process. Originally, the Solvay process have RP at 5 and BP at 4. 5 moles of reactants are required to generate 1 mole of product. Also, 4 moles of byproducts are produced with just 1 mole of product. Then let me check the new column. So R, let me check -1, minus signs, -1 and -2, so totally 3. 3 over 1 is equal to 3. How about byproduct? There are no plus, no plus, no plus, and only plus is found here, which comes from calcium chloride. So 1 by 1 is equal to 1. Then here's our success. After process synthesis, you have decreased the RP value and BP value at the same time. You have compared between Leblanc process and Solvay process. Also, you have improved the Solvay process by using the generation consumption analysis. And here is another example for ammonia synthesis. Leblanc and Solvay was for making sodium carbonate, right now ammonia synthesis. So let me check it. The first step 1, balanced CLE, and methane plus water is going to carbon monoxide with hydrogen. This carbon monoxide is used for making another hydrogen. So actually the first two reactions are adapted for making hydrogen gases, and those hydrogen gases is used for making ammonia in the presence of nitrogen. So right now we have all stoichiometric coefficient. Then let's go to the step 2, stoichiometric coefficient table. Compounds: methane, water, carbon monoxide, hydrogen, the same thing, carbon dioxide here, and the same thing, nitrogen here, the same thing, and ammonia, the final product. Then let's get some stoichiometric coefficient from the chemical reaction equations into stoichiometric coefficient table. For the reaction 1, something like that. R2, something like that. R3, something like that. And in the last column, list the net summation of those stoichiometric coefficient. Then target setup. Okay, you can find carbon monoxide and hydrogen. Carbon monoxide is toxic, hydrogen is explosive gases, so I'd like to remove net generation or consumption of carbon monoxide and hydrogen gases. So put the so the blank list includes carbon monoxide and hydrogen gases, and those two compounds are related to all reactions. Look at that, hydrogen, all reactions. So you should put the weight factor for all reactions. So Chi1 for R1, Chi2, Chi3. Then let's go to the step 4, Chi calculation. For the carbon monoxide, Chi1 minus Chi2 should be 0. Actually already 0, but right now Chi1 minus Chi2 0, because after the weight factor is applied to the reaction 1 and reaction 2 and reaction 3, this value cannot be 0. So you should add the equation about the carbon monoxide. The second reaction is 3 Chi1 plus 1 Chi2 plus minus 3 Chi3 should be 0. Then right now, two equations, because there are two compounds in the blank list, and then three unknowns because three reactions are involved. Then degree of freedom is equal to 1, so we cannot solve this problem. In this case, you should fix one of the unknowns or one of the weight factors. I'd like to choose methane as the basis, and then in that case, Chi1 is equal to 1. Because, okay, chi1 is equal to 1. Look at that. The stoichiometric coefficient of CH4 only in the reaction 1 is 1. So the wave factor should be 1. Only in that case you can keep the CH4, the stoichiometric coefficient of CH4 as 1. So basis is equal to CH4 means chi1 is equal to 1. Then right now, two unknowns, chi2 and chi3, with two equations. Then you can calculate the values of chi2 and chi3. Okay, so let me apply these wave factors. I mean step 5, process synthesis. Then chi1 just 1, nothing change. How about the reaction 2, nothing change. But reaction 3 is changing. Minus 3 by 4 over 3 is going to minus 4. Then also minus 1 is going to minus 4 over 3, plus 2 is going to plus 8 over 3 by applying the wave factor 4 over 3. Then calculate the net summation of the stoichiometric coefficient. Okay, let me compare the values of RP and BP between those two tables. These tables for before the process synthesis. This table is after the process synthesis. Then let me start with the original one. So reactant, check the minus sign. 1, 3, 4. This is R is 4 and the product is 2 moles. Then 4 over 2 is going to 2. How about byproduct? Let me check positive sign. Hydrogen byproduct, carbon dioxide byproduct. So 2 per ammonia 2 is equal to 1. However, for the new process after the process synthesis, R is the summation of minus thing is going to 13. No. So the summation of this one minus 1 is the R and product is 8 over 3 and the result is 13 over 8. Please calculate it. And this value is less than number 2, the original value. How about P? Side product or byproduct. Let me check plus sign. So this one, CO2, only side product is CO2. So 1 divided by 8 over 3. Then BP is going to 3 over 8, which is much less than number 1. That is the value of the original process. So successfully we have improved the original ammonia synthesis process by using the generation consumption analysis and plus process synthesis. This is the new subchapter about the atom economy. Subchapter 5, atom economy. Actually, this subchapter 5 includes two parameters. The first one is atom economy and the other one is process economy. In the previous subchapter, you have learned about generation consumption analysis. And in generation consumption analysis, I have provided two measures to evaluate the chemical processes, RP ratio and BP ratio. In this subchapter 5, I have provided two additional measures to evaluate the chemical processes. Those things are atom economy and process economy. Okay, let me start with atom economy. Early 1990s, Roger Sheldon and Barry Trost suggest the atom economy. The atom economy is a measure of the efficiency of a reaction pathway in converting reactants to products. Actually, the meaning is the same as the RP ratio. You have learned about that in the previous section, GCA, Generation Consumption Analysis. So, here is the definition of the atom economy. Fractional atom economy is equal to desired product per all reactants. So I can say this parameter as PR ratio. Actually, this PR ratio is the inverse of RP ratio you have learned from the previous section. However, there is one more difference. In the RP ratio or BP ratio used in the generation consumption analysis, we have used moles. Please remind, we have used the stoichiometric coefficient for calculating RP ratio and BP ratio. The meaning of stoichiometric coefficient is moles. So RP and BP ratios are molar ratios. However, in the fractional atom economy, PR ratio is not the molar ratio, but the mass ratio. So definition is like that. Mass, I'd like to emphasize the word mass. Mass of desired product per total mass of reactants. In the equation, fractional atom economy can be described by like that. This is stoichiometric coefficient of product, and this is the summation of the stoichiometric coefficient of all reactants. Plus, we have one more terms here, molecular weight. Molecular weight of product and molecular weight of all reactants. So, actually, if you should define the PR ratio in moles, maybe nu sub p per minus sigma nu I is enough. However, in this definition, we should use the mass. So you should multiply the molecular weight of each species by the stoichiometric coefficient. Okay? So that is the definition of fractional atom economy. And this parameter is the mass ratio instead of molar ratio. Okay, let me try to understand the concept of atom economy by using the examples. I'd like to use the Leblanc process and also Solvay process previously used in the generation consumption analysis. At that time, we have calculated the RP and BP ratio in moles. So here is the net reaction in Leblanc process, and sodium chloride, calcium carbonate in presence of sulfuric acid and carbon. Then finally we could obtain a desired product, which is sodium carbonate, and then byproduct HCl, CO2, calcium sulfide. Okay, let me make some table. So in this case, we have 1, 2, 3, 4. 4 reactants is listed in the first column plus desired product. In this calculation for the mass PR ratio for atom economy, we will not take care of the byproduct. So I skip the byproducts in the compound. Then the second column is, of course, stoichiometric coefficient. It is a kind of the stoichiometric coefficient table used in the generation consumption analysis. But in this case, we have used the overall equation instead of the stepwise equations. Then like -2, -1 for sulfuric acid or something like that, +1 for sodium carbonate. And then we need to have information about the molecular weight for sodium chloride 58.5, sulfuric acid 98, and sodium carbonate 106. The product of stoichiometric coefficient and molecular weight is going to mass. So let me check the units here. This is stoichiometric coefficient, so the unit could be considered as mole, and the molecular weight have the unit at a gram per mole. So the product of stoichiometric coefficient and molecular weight is going to here moles and then grams, so mass. So in the last column you can find the mass of each compound consumed or generated during the process. So by definition, PR ratio or fractional atom economy, this one, is equal to product mass from here, and the summation of those four reactant mass here. So, and also you should remove the minus sign, and then the resultant answer is 0.31. What does it mean? 31% of the mass of reactant is converted to the mass of product. Okay, so the higher values, better. It is a kind of the inverse version of the RP ratio you have used before, but we should use the mass instead of moles. Okay, for comparison, let's go to the Solvay process here, and after the process synthesis, then we have simplified the Solvay process, and this is the overall chemical equations. Sodium chloride, calcium carbonate, only two things are used as the raw materials, and the final product is sodium carbonate and then calcium chloride as the byproduct. So fractional atomic economy or PR ratio in mass is equal to product 106, the same like that, and then reactant, only two electrons are involved, sodium chloride and calcium carbonate, so 107 and 100 here. Then the value of the fractional atom economy is 49%. About 50% of the raw materials is converted to the product. So we could say Solvay process is better than the Leblanc process because more amount of the raw materials is converted into the product. So I can say higher fractional atom economy is going to more cost efficient process. We are still on the atom economy, and here is the second example for 4-ADPA synthesis process. For amino diphenyl amine, shortly 4-ADPA, is the compounds to reduce degradation of rubber tires, and then we'll make them. So here I'd like to introduce two different processes to make the same thing. The first one is traditional process having 4 steps or 4 reactions, and the other thing is developed in early 1990s as the new process, and only 2 steps is involved in this new process. So I'd like to compare between those traditional and new processes in terms of GCA and also atom economy. Here is the calculation. Here is the tables for calculation. Traditional process and new process. So first I'd like to use GCA. And this is the stoichiometric coefficient table. First column, I have just listed all compounds involved in those 4 reactions in traditional process. And because we have 4 reactions, so there's 4 columns there. And then fill out the stoichiometric coefficients. And then in the last column, we have the net summation of the stoichiometric coefficient for each compound. Then by using these values, you could calculate the molar RP ratio. So in this case, the desired product is 1 mole, and then to get the 1 mole, you need to have 7.5 moles of reactant. You can find the reactant at the minus signs, right? Okay, how about new process? The number of compounds are reduced, like 6 compounds, and only 2 equations are there. Then stoichiometric coefficients is here, and in the last column we can calculate another RP ratio. So the final product is 1 mole. For making this 1 mole of final product, you need to have 1, 2, 3, 4 moles of reactants are required. So RP ratio is 4. In terms of RP ratio, the smaller value is better, of course, right? Because it means a smaller amount of reactant is required for making 1 moles of product. Okay, so 7.5 for traditional process and 4 for new process. So I can say that new process is better than the traditional process in terms of RP ratio. At this time, I want to use the atom economy, and I will calculate the fractional atom economy, or PR ratio, PR mass ratio, instead of RP mole ratio. So, as I said before, in the atom economy calculation, what we need to have is only reactants and desired products. I don't take care of byproducts and intermediates. So let me extract the reactants from this long list of compounds. Minus sign indicates the reactants. 0 means intermediate. Plus means product or byproduct. So C6H6 reactant, because we have -1. How about Cl2, right? And HNO3, right? So we have 3 here. And the next one this is the intermediate. And this one is -1. So it can be considered as the reactant here. And K2CO3 minus 0.5 as the net summation. So this is also reactant here. And what is the next -1? Going downward, and then -3 for hydrogen. So hydrogen here. So all reactants are listed in this column. Plus, one more thing, desired product. 4 ADPA is here, +1, and then it is going to there. Also, at the same time, stoichiometric coefficients are moved here. And to convert the stoichiometric coefficient to the mass, we need to have the information about the molecular weight. Then in the last column, you can find the mass information about each compound involved in this process. In the same way for the new process, and then I'd like to calculate the PR mass ratio. So product 184 and the summation of all things here, and then it is going to 45%. On the other hand, for the new process, the same amount of mass of 4 ADPA is here, and only 3 things are reactants here, then 84%. So it means new process is better than the traditional process because 84% of the reactant mass is converted to the product. However, the traditional process economy, I mean the atom economy of traditional process is just 45%. So I can say the new process is much better than the traditional process in terms of fractional atom economy. We are still on the subchapter 5, atom economy, but right now I'd like to change the topic from atom economy to process economy as the second measure for the chemical processes in this chapter. So process economy is closely related to the money. What is the monetary difference between the value of the product and the cost of the raw materials? You will calculate the earning from the product and cost from the reactant, and then finally you should get the information whether I can lose money or I can earn money. Okay, here's the example. What is that? Solvay process for making sodium carbonate. Two reactants, calcium carbonate plus sodium chloride is going to desired product and byproduct. So here is the question. Calculate the cost of sodium chloride to produce 1000 tons sodium carbonate per day by Solvay process. Okay, one there is very important information is here. To produce 1000 tons sodium carbonate per day. So this is considered as a basis for this question. Anyway, we will touch the sodium carbonate and sodium chloride here, because this question is just related to two compounds, not for calcium carbonate, not for calcium chloride. So I will touch those two compounds. One more thing. We will calculate the money, and usually the cost of materials are reported in the unit of dollar per ton, like that. $95 per ton sodium chloride or something like that. So we need to convert the stoichiometric coefficient or moles to mass. So the first step we should do is to convert moles to mass. So stoichiometric coefficient of sodium carbonate, the target material here, with molecular weight of the same molecules is going to mass. So right now 106 grams sodium carbonate is produced. At the same time, we need to have minus 117 grams sodium chloride by multiplying the stoichiometric coefficient and molecular weight. It means 117 grams sodium chloride will be consumed for making 106 grams sodium carbonate. But the question is saying about producing 1000 tons per day instead of 106 gram sodium carbonate. So we should scale up this amount into 1000 tons. So here is the proportionality equations, like sodium carbonate to sodium chloride is 106 gram from here, and 107 gram is consumed from here. Then, which is equal to 1000 tons of sodium carbonate per day existing in the questions, and then unknown. What tons sodium chloride per day is required for making 1000 tons sodium carbonate per day? So we should get the value of this unknown. From the proportionality relationship, this unknown or sodium chloride consumed rate is equal to this one by the ratio of this one. 1000 is there, 106 is there. Then it is going to some value. about the amount of or rate of sodium chloride consumption? The answer is minus. Minus means consumption. So minus 1104 tons per day. Okay, let's go back to the calculation. This second term is so-called scale factor, or shortly SF. Scale factor is obtained by dividing bases, in this case 1000 tons sodium carbonate per day, per mass quantity 106 for the same material, sodium carbonate. And then this is the scale factor. By using the scale factor, you could scale up the values obtained from the chemical reaction equation to the basis level. So anyway, again, 104 tons per day of sodium chloride should be consumed or should be required for making 1000 tons sodium carbonate per day. So here is the value, and as the third step, it's time to convert the amount into dollar, the money. So the cost of sodium chloride is like that, $95 per ton sodium chloride. This information could be easily obtained from chemical market reporter. Then the product of those two things, then let me check the unit. Tons sodium chloride per tons sodium chloride. Then the remaining unit is dollar per day is here. Dollar per day. And the value is about $100,000 per day is required to producing 100 tons sodium carbonate per day. Okay, here is the second question for the same process. Let me change the pen into the laser pointer. Okay. For the production of 1000 tons soda ash means sodium carbonate, soda ash per day, the same basis, what are the required feed rates of limestone and salt? Limestone indicates the calcium carbonate. So we need to calculate everything. Net reaction is like that, which is the Solvay process. Actually, modified Solvay process we did by using the process synthesis. And in this case, scale factor is 1000 ton per day per 106 gram. The basis was the sodium carbonate. And then let me try to make a table including all information required for the calculation. The first column, compound, 4 compounds related to the equation, to the overall equation. And then stoichiometric coefficient, this is the molar information. And molecular weight is the conversion factor from moles to mass. Therefore, this is the mass column. And then it's time to scale up those just chemical reaction equation level into the basis level by multiplying the scaling factor. So 107 by scaling factor, 100 by scaling factor, 106 by scaling factor is going to 1000. That is the basis, of course. And the other thing, calcium chloride, to scale up. One more line is required, column is required, because we need to have the information about the cost or value. This one. And then in the last column, you can find the total value, cost or values of each compound. So $105,000 per day is required. At the same time, $82,000 per day for calcium carbonate is required. But I will sell the sodium carbonate into the customers at this value like 105,000. So let me try to get the summation. Those three things. At the very first time, we didn't think about the calcium chloride is valuable. So we have just discarded the calcium chloride. This is assumption. Then in that case, we need to sum those three things. Then finally, minus 82,000 without calcium chloride. In that case, oops, deficit. We lost the money from the chemical processes. However, surprisingly, the byproduct is very valuable, more than the sodium carbonate. The value of calcium chloride is $250 per ton, but which is higher than the cost of value of sodium carbonate 105. So we should sell calcium chloride as well as sodium carbonate, and then plus this value, then finally we can reach profit. Only when we sell or marketing the sodium carbonate and calcium chloride, then we can earn money. This is the process economy, and from the process economy analysis, we could recognize whether we can earn or lose our money from the chemical processes. You have already learned all contents of chapter 1 from the viewpoint of concepts and basics. From this slide, I'd like to use of all concepts and all methods to compare and to select the chemical process. I'm your boss in some chemical plant, and then my order is to make decisions about raw materials, products, and reaction pathways in the production of 6 carbon compounds, in this case benzene. I have a lot of benzenes, and then we should make something from the benzene, and then we should estimate which product is better than the other in terms of atom economy and also process economy. Benzene here is a 6 carbon compound purified from petroleum. What are some useful 6 carbon products we might make from benzene? A lot of choices are here and there, but in this big example, I'd like to compare between adipic acid production or catechol production. Okay, let me start with the conversion of benzene to adipic acid. The adipic acid is my first choice, and then we are going to the catechol production. Then we'll compare those two things. Benzene is going to cyclohexane, then hexanon, then finally it is converted to adipic acid. We have already known the balanced equation for those 3 steps. Step 1, this one, this, and step 3. So let's try to make the stoichiometric coefficient to understand the whole process of the conversion of benzene to adipic acid. As you know, in the first column you have all compounds, and you have 3 reactions, 3 more columns here and there, and stoichiometric coefficients are here. Then in the last column you can get the net summation of the stoichiometric coefficient. So let me check it. Hexane -1 reactant, and then hydrogen also reactant, and then the cyclohexane, this guy, is produced, but from the information about the net sum, zero net sum, then we recognize this one, cyclohexane, is the intermediate. Then oxygen is introduced as the reactant, and then cyclohexanone is produced, but this is the intermediate. Lesson from number 0. Next one is nitric acid is introduced, -2, and then the product is finally adipic acid here, and then nitrogen oxide and water. That is the reaction pathway for the conversion of benzene to adipic acid. So here's the summary for the understanding of this process. 0 net generation consumption of cyclohexane and cyclohexanone. They are intermediate. And waste product is, well, byproducts are NO and H2O. You know, NO is not good. NO is causing the formation of micro dust, well, very small dust. So I hate this NO, and I will try to remove this NO, but unfortunately no commercial process to avoid the generation of that nitric oxides for making the adipic acid. So we should have nitrogen or nitric oxide in the product stream. So please calculate the RP molar ratio or BP molar ratio by yourself. And then just I'd like to go to the calculation of atomic economy here and process economy. So here's the table for calculating those two measures. Those 4 things are reactants, and those 3 things are products. NO and H2O could be considered as the byproduct. The stoichiometric coefficient, molecular weight to convert the moles to mass, and then what you need is the scale factor. So in this problem, the scale factor is obtained from 15,000 kilogram benzene per day per 78 gram benzene, and then it is going to 192.3. So this column is going to that column by multiplying the scaling factor. At this column we are thinking about the chemical reaction equation level. However, by multiplying the scaling factor, then we are thinking about the amount in the level of the basis. So, something like that. To produce, to consume, by using 15,000 the kilogram benzene per day, how kilogram per day of H2O2 and nitric acid is consumed, required, and also how kilogram per day of adipic acid is produced. In this case, about 30,000 kilogram adipic acid per day is produced by using 15,000 kilogram the benzene per day. So basis is very important thing, especially for scale up and also especially for the comparison. In this column we have the cost or value, and then finally in the last column you can get the summation of those dollar for each compound. Then okay, let's calculate the atomic economy or more PR mass ratio. So we can use this column or also we can use this column. Anything is okay. Then product per reactant. So product 146 for the adipic acid. And the other thing is the all of them that they are reactant here. Then 60% of the mass of reactant is going to the mass of product. Not bad. How about process economy? Then here is the cost. Oxygen is 0 because we use the air, and then nitric acid like that. So those four things are cost, and this is the earning. So the net summation of money is about a little bit less than $30,000 per day earning. So in terms of process economy, we could obtain net benefit. Net benefit. We can get the money. So this is the adipic acid process, which was our first choice. Okay, so then let's go to the second choice. I'd like to produce catechol instead of adipic acid. So here here are the balanced chemical reaction equations. So benzene to isopropyl benzene, or cumin, it is called cumin. So benzene is going to cumin, and this cumin is used for making cumin hydroperoxide. So maybe cumin is the intermediate. Then this hydroperoxide as the intermediate, another intermediate, is converted to the phenol and acetone. And then this phenol is going to the catechol. Please think about the acetone. Of course, acetone is byproduct, but that is the useful solvent. So you can sell the acetone even if it is byproduct. Also, of course, catechol is our target desired product. Then here's the stoichiometric coefficient table. So as you know, we have four equations and then a lot of compound. Then you can understand which one is the intermediate, which one is the reactant, and which one is the product and byproduct. So we'll consider the desired product, which is the primarily the catechol but also acetone. So please calculate the molar RP ratio and BP ratio by yourself. Let's go to the economic evaluations. So here is also the big table for calculating the atom economy and process economy. Still, we have the same basis, which is the benzene, and then the same amount is consumed for the process, minus 15,000 kilogram the benzene consumed per day. Then we could calculate every other things. So atom economy, we could use again this value and this value. Anything is okay. So product per reactant and product desired product, this one 110, and then for those four guys are considered as the reactant, so it's going to the denominator, so 60% atom economy is obtained. Also, let me go to the process economy. Those are cost, and those two things, again, this is the catechol and this is the acetone. We will sell those two guys to the customers. Then summation of all money, that is going to about 90,000 profit. Plus means profit, minus means deficit. So let me compare with the previous example, which is the adipic acid process. Right now we are making the catechol, but in the previous calculation we're thinking about the adipic acid production. So in that case, one bad thing, nitric oxide waste is produced, so it's not good. How about atom economy? 60%. This value is very similar to the atom economy of the production of catechol. So almost the same. So we cannot decide which one is better. However, let's go to the process economy. About the adipic acid production process, we will earn the money less than $30,000 per day. However, if you want to make the catechol plus acetone, you will earn money at $90,000 per day, 3 times more benefit. Well, profit would be going up. So we should choose the production of catechol than the production of benzene to adipic acid process. So the catechol wins against the adipic acid because we can earn more money. So until now, we are thinking about the benzene as the raw materials. So we have compared between two processes. The first one is adipic acid production process from the benzene, and the second process was the catechol production process from the same thing, benzene. So by using the atomic economy plus process economy, we have decided the catechol production is better than the adipic acid production in terms of atomic and process economy. But there is some concerns about the benzene as the raw materials. Petroleum is a non-renewable resource, and also benzene is produced from this non-renewable resource. So there is some the environmental problems. Benzene is also carcinogenic and sometimes causes smoke. Also, sometimes we would have nitric oxide as the byproduct, and these gases contribute to ozone depletion and the greenhouse effect. So, I'm still your boss, and then I'd like to ask you these questions. Could we replace benzene with a raw material from a renewable, I'd like to emphasize the word renewable resource to make the same 6-carbon product? That is to say, adipic acid catechol. So the good candidate for the raw materials, which is very renewable, is glucose, this one. Glucose is non-toxic, and glucose made from the renewable resources like corn, popcorn, corn. And also, the glucose is chemically more similar to adipic acid. Adipic acid is here, and catechol here, then it's benzene. So, look at the structures. Glucose are similar to the adipic acid or catechol than benzene. So let's try to use the glucose instead of benzene. So in the case of benzene processes, we considered the adipic acid production process at the very first time, and then we went to the catechol production process. So the same thing here. The first one is the conversion of glucose to adipic acid. Reaction 1. Genetically engineered bacteria, E. coli, to convert glucose to muconic acid. Glucose oxidation, muconic acid with CO2 and H2O. That is the kind of biochemical reactions by bacteria. And then this muconic acid is converted finally to adipic acid. So muconic acid is considered as the intermediate. This is the muconic acid and this is the adipic acid. Then for calculating atom and process economy, we have a big table for required information. Then you can calculate atom economy and process economy. So please try to do it by yourself. Anyway, I'd like to emphasize one thing here. What is the scale factor SF to convert this column to scale up column, this column? So let me go back to the benzene processes to compare between the adipic acid production and catechol production processes. We have fixed the benzene as a basis for comparison, right? At that time, 15,000 kilogram benzene per day is used for making those two processes. But right now, the raw material benzene is replaced by glucose. So it is difficult to keep the basis. So we should change the basis from the reactant to product. Okay, so here's the basis. This is the product or adipic acid, and adipic acid is produced at 2,100 kilogram per day. So the scaling factor is calculated by this amount by this value, then going to 192.5. By using this scale factor, you can convert this column to this column, scale up column. Why should we choose this a kind of weird value? Because when the benzene used at 15,000 kilogram per day, the produced adipic acid amount was this in the previous example. So we will compare between benzene based and glucose based processes in terms of fixed adipic acid production rate. Okay, so this value is coming from the previous example. Okay, so anyway, you could calculate the fractional atom economy or PR mass ratio. This is 20%. Can you remember the atom economy values from the benzene processes? About 60%. The atom economy was estimated at the very low value when compared with the benzene process. And process economy was estimated at minus $5,400 per day. So maybe we will not decide to select this process because we will lose money by adapting this process. Plus one more thing, CO2 byproduct, it's not good. Of course, the second glucose process is for the production of catechol. And this is the balanced chemical reaction equation. And then here's the table for the economy calculation. And then you can calculate like that, also less than 20%. However, the good thing is we can earn money even if we are using the renewable resources. About $50,000 per day earning. But still we have CO2 byproduct. One more things. Okay, so what is the scale factor? Scale factor is this one. This is catechol amount or catechol production rate, which is obtained from the previous example based on benzene. So the same amount of production of catechol is used as the basis. And then 110. So this value divided by this value is going to the scaling factor. Okay, that's it. Then let me summarize and compare all of the processes. We have 4 processes here. The first 2 processes are benzene-based one. Of course, adipic acid and catechol. The second group is based on glucose for making adipic acid and catechol. And the basis was determined by product, like adipic acid like that, catechol like that, the same value, same value. And then for evaluating the processes, let me compare the values of atomic economy and process economy. So benzene-based processes have very high values of atom economy, like about 60%. However, when the benzene is replaced by glucose, the atom economy is going down about 20%. So from the viewpoint of atom economy, the benzene process is better than the glucose process, unfortunately. However, about the process economy we should consider. So about 30,000 for the conversion of benzene to adipic acid. And the second one, the conversion of benzene to catechol was better than the first one because 90,000 earning. The third one, we should kill it because we will lose money. However, the fourth one have on still have an opportunity, about 50,000 the profit available, even if we are using the renewable resources for the raw materials. So something like that. So maybe my primary choice would be the second one, benzene to catechol, but the secondary choice would be glucose to catechol in this fourth law. Also, we should consider about the waste. The first process of benzene to adipic acid having NO is terrible. I don't like it. How about CO2? It's not good also. So we should think about the production of CO2. And CO2 production is closely related to additional cost because we should remove the cost, remove the CO2 from the outlet stream. What else we need to consider? What if the energy for the benzene process is supplied by burning fuels and thus producing CO2? So I'd like to say about CO2 issue. So from the viewpoint of CO2 from this table, of course, benzene is better than glucose. However, this process is the high temperature process. Then you should heat the whole reactors. In that case, we need to think about additional CO2 production. Sometimes this CO2 amount is larger than the CO2 for the glucose. Waste calculations must consider energy requirements as well as raw material requirements. Okay, that's it. This is the end of chapter 1, and here is the summary. Here is the key content of chapter 1. What is the first one? Can you balance the chemical reaction equation? That is the first keyword. And then the second one is the evaluation of the chemical processes by generation consumption analysis, including RP ratio and BP molar ratio. Also, atomic economy and process economy are measures of the chemical processes. That's it. And here is homework. Problem 1.15, 24, and 33. So you can find the copy of these problems in your blackboard. That's it for the chapter 1.